Welcome to the segment on STM32F411XC or XE clock tree. Now, before you freak out seeing this diagram, it is not that difficult to understand. Now, I have seen a lot of confusion happen with setting up the clock for higher end microcontrollers. So we will go slowly in this chapter and we will not move to the next section until we understand this completely. And if you look at this clock tree if you can separate out the different units in the clock tree, this diagram becomes much more easy, which we shall do moving forward. So this is just to give you an idea of what the clock tree looks like. And we have different components of this going to various parts of the microcontroller. And let's proceed from here, and we will keep coming back to this clock tree diagram to explain what is really going on. So just bear with me, and by the end of this segment, I promise that all of this will become very easy. So the clock controller provides a high degree of flexibility to the application in the choice of external crystal or the oscillator to run the core and peripherals at the highest frequency. Now, why do you think the clock tree for a high-end microcontroller looks so complicated? There are some reasons behind it. It is not for nothing that the clock tree would be made so difficult. First of all, you have the option. So first of all, you have the option to choose the right clock for your application. Okay. So there are various clock sources that are mentioned here in this diagram, and you can choose between multiple clocks. That is one thing. Secondly, such a clock tree or such an architecture is made for purposes of power saving also. That is, you could turn off the clock to different sections of the microcontroller. So you could turn off the clocks to different segments or sections of the microcontroller, thus conserving power. And since the 32-bit controllers can operate at pretty high frequencies, we are going to work on 84 megahertz. But then you can go up to very high frequency. You can go up easily to 100 or 150 megahertz for other processors or other controllers, other families of controllers. So naturally, the architecture has to be more complex because the purpose that this particular clock tree serves is much more involved and much more complicated than a simpler microcontroller like an 8-bit controller. Now, we already have studied about the different buses. So AHB and APB1 and APB2 buses. Okay? So this particular clock system supplies the clocks to all these buses. And once we understand this diagram, we will know what is really going on and how the different the clock is distributed between the different buses. A few things that you need to immediately understand to better translate what is going on in the clock tree is the clock tree comprises of multiplexers, it comprises of some gates. So these are AND gates. So we'll not talk about that. So it right now. So it comprises of multiplexers, it comprises of frequency dividers, it comprises of, so frequency dividers we also called prescalers, so they are nothing but frequency dividers. Okay. And then you have clocks actually, so internal and external clocks which actually generate your clock frequency. So clocks, and you have various clocks in this system. Okay. And that is pretty much it. And you have the VCO, which is again an extremely important component of the, and then if you have the VCO, then you will of course have the PLL. Okay. So these are the components of the clock tree for this particular microcontroller. Now, if we understand the interaction between these components, the clock tree will become extremely easy for us. And since this is a bare metal course and we are writing code from the scratch, we will have to understand the clock tree from the scratch. We are not using any configuration tool for configuring the clock. We are going to do it from the scratch. Now, so these are certain terminologies, and these are the most complicated parts of the clock tree, that is the PLL. So you have a VCO, you have a PLL. So these are the most complex parts of the clock tree. So this is like solving a puzzle basically. You have to choose a particular clock source, and then depending on the clock source, you have to route that particular clock to the PLL, and then from the PLL you have to pull out that particular clock source and feed it into different buses and so on. So we'll see all of that. Okay, all of that will be very clear to you after this. So moving on to the next slide. We were here actually before, so let's drop this out. So we were talking about the clock controller providing a high degree of flexibility to the application in the choice of external crystal or the oscillator to run the core and peripherals at the highest frequency. Now you have the choice of selecting an internal oscillator or an external oscillator, and guarantee the appropriate frequency for peripherals that need a specific clock like USB, OTG, FS, I2S, and SDIO. So again, different parts of this particular SoC, that is the microcontroller, will need different clock frequencies to operate. Now all of this is done through the clock tree. Now this part of the diagram, that is 4 to 26 megahertz oscillator, this is what we are going to use. So we are going to use the external oscillator to set up the clock here. So several prescalers are used to configure the AHB frequency, the high speed APB and the low speed APB domains. So prescalers means, suppose you configure the clock say for 100 megahertz, but this particular say APB1 can operate in only so say the low speed APB1 domain can operate only in 50 megahertz. So if you have to feed it to that domain APB1, you have to of course divide this by 2. So there is a divide by 2 block prescaler which you have to activate, so that even though the clock frequency for the processor is 100 megahertz, you get 50 megahertz here, because this one cannot go above 50 megahertz. Okay, this will not function above 50 megahertz. So there are different buses again which operate at different clock frequencies, and we have to route the clock and we have to set the clocks accordingly. This is in brief what the clock system does in this microcontroller. So the high speed external clock signal HSC can be generated from 2 possible clock sources. Okay, that is the HSC external crystal or ceramic resonator, which this is the setting that we are going to use, HSC external crystal and HSC external user clock. We are not going to use this. We are using HSC external crystal or ceramic resonator, which is available on the evaluation board, that is the discovery board. And the HSC has Now the question might arise is that, if the controller has an internal clock, okay, why does it need an external crystal? Now the internal clock that we have in the controller is not very accurate. That is, there is a drift. There is some phase noise and there is a drift in this clock. So if you want an extremely accurate clock, we know that crystal oscillators provide extremely accurate references. So we will be using the external clock to use it to generate our clock. But then we have to pass it through a lot of hoops so that that frequency is actually multiplied up to what our requirement is, because the external crystal frequency is very low. Though it is extremely accurate, but it is extremely low. So our external crystal frequency is only 8 megahertz. Now from this 8 megahertz, we have to bump it up to 84 megahertz in our case. So obviously there has to be some circuitry coming in the middle to do that. So the 8 megahertz is going to provide the stable clock, and from there the VCO, or the voltage controlled oscillator, is going to bump it to a higher frequency. But then again, the VCO is not stable. So we'll see all that. So how the VCO clock is kept stable through a PLL and things like that. So this one, if you go back to the diagram here, this is the HSE clock that we'll be using, and this is where the crystal is connected. Okay. So this is where the crystal is connected, and this is the HSE clock that we are going to be using. So we'll have to use the HSE clock. We'll have to use the PLL here, and then route this clock out to this particular multiplexer. So we'll see all that. Let's sort this out. So like we were saying, like we were discussing, the HSI clock signal is generated from an internal 16 megahertz RC oscillator and can be used directly as a system clock or used as a PLL input. So the PLL input this clock can be used by the PLL also. However, even with calibration, the frequency is less accurate than an external crystal oscillator or ceramic oscillator. So when the processor starts up, it uses this clock by default. So when you power on the board and you have not, say, configured the PLL to a higher frequency, still you are able to use your discovery board. And that happens because by default, the controller starts using this particular 16 megahertz HSI RC clock, okay, which is an RC oscillator, and it's not stable. Nevertheless, it does your job, at least to bring up the controller and say, set it up for set up the peripheral and the memory and the startup and everything. Okay, so that's how it is. And you can leave this, if you are actually using your controller to learn basic things, you can actually leave this clock as it is, and it will do your job. Okay, it will more or less do your job as expected. But then this clock is not stable. So if you want to use some peripherals like your USB for one, then this clock is completely out. You may feed it to the PLL and bump up the frequency to higher frequencies, but since this clock itself is not stable, the behavior is not well defined. So we will not be using this clock after setting up the PLL. We will disconnect this clock. There is another clock called LSE clock, which is generated using a 32.786 kilohertz low speed external crystal or ceramic resonator. It has the advantage of providing a low power but highly accurate clock source to the real time clock peripheral RTC for clock, calendar, or other timing functions. So there is another clock here, external crystal. So this crystal is again separate from the crystal that we have been talking about, and that is used. It's a 32.768 kilohertz low speed external crystal, and it has the advantage of maintaining a real-time clock on the controller. So the controller also has a real-time clock with calendar function. So if you have an application which needs a real-time clock and calendar functions and everything, we will go for this clock. Now the LSI-RC acts as a low power clock source that can be kept running in stop and standby mode for independent watchdog and auto wake up in it. The clock frequency is around 32 kHz. So this is another clock which is used for, this keeps running in the stop and standby mode. So if the processor is in standby mode or it is stopped, then and for the auto wake up unit, this clock can be used. I've just kept it here to mention those, but in this version of our course, we are not going to use these clocks, but it is better for you to know about this. So we have LSC oscillator and LSI-RC, and these are all parts of the clock tree only. I've just cut those diagrams and I pasted here, but these are parts of that particular diagram only. We have already started breaking down the diagram into separate components so that it is easier for us to understand and follow. So see, since we are not using these two clocks for our application, we can just rule these two sections out for now. So going forward, after a system reset, the HSI oscillator is selected as a system clock by default. A switch from one clock source to another occurs only if the target clock source is ready. Clock stable after startup, delay or PLL is locked. So like we discussed a little while ago, we are using the HSI clock signal as default. Okay, but and then from the HSI, say this is the HSI clock, supplying clock to the controller or the internal components, and so this is the PLL that we have to switch to. Now while the HSI clock is running, we have to configure the PLL, and at that point the PLL will not be connected. Say the PLL is not going to be connected at that point, so it is disconnected here. Say it is disconnected. Only when after setting the PLL, it takes a while for this clock to stabilize. And until this clock stabilizes, we don't disconnect the HSI, okay, and connect the PLL. So once the clock stabilizes, we cut this connection and we join the PLL to the controller, and the status bits in the RCC control domain, that is RCC-CR, indicate which clocks are ready and which clock is currently used as the system clock. And we'll see these registers in detail later. So the status bit in the RCC-CR indicate which clocks are ready and which clock is currently used as the system clock. Now let's see if we can have a look at this register in the reference manual. So it is RCC_CR. So let's see if we can find that out. So this is the chapter on clock. Let's erase this. Okay. So let's go down. So we hope to find those registers here. So that's my guess. So let's see if we can find those registers, that is RCC-CR. Okay, here. So come down. So let's assume that we are looking at this chapter newly, and see here. This is the register that we are talking about. That is RCC-CR, and this will give you the status of all the clocks which are ready and which are not. For example, if the PLL is ready or not. So we'll have to check this bit before we connect the PLL. To power the HSC clock on, HSC clock off, all of that is going to happen through this particular register. So this is a very important register for setting up the PLL. So make a note of this particular register. This is, we will revisit this register going forward, and it is in page, the diagram is on page 102 in the reference manual. Now, for us to understand the clock tree on the STM32F4, we have to understand the PLL block. The PLL stands for phase locked loop, and the objective of the PLL is to create a programmable waveform with very low phase noise and hence an accurate, consistent and stable frequency output. Now, when we say phase noise, uh, it means deviation or uh, so suppose you have, just imagine this is a clock say of 100 megahertz that we need to generate. So the objective here is to keep this clock at 100 megahertz. So there will be various factors like temperature and other factors which will cause this clock to shift in its frequency. It could be 101 megahertz, or it could go on the other side, go lower, say 98 megahertz, and so on with time. And we do not want this deviation. So we want the clock frequency to stay stable at 100 megahertz. And if there is any deviation, it should be immediately corrected. And that is the job of the phase lock loop. Now, so the first, generally the PLL is used to create accurate, consistent, and a stable frequency output. And the second point is the whole purpose of the PLL is to keep the VCO in the PLL not to drift. So this is the voltage controlled oscillator inside the phase lock loop. And the objective is to prevent this thing from drifting. That is, as we saw, the frequency, whatever the VCO generates, should be constant. It should not drift. Now, its PLL is used for frequency synthesis. That is what we are going to use it now for. It is also used for demodulation and modulation, FM discrimination, tone decoding, tuning control, and clock recovery. So we are not going to see any of this. Here, the only application of the PLL is used to synthesize a frequency of our choosing. So whatever frequency we program it for, after the PLL is set, it should not deviate from that frequency. For us, it is in the case of our discovery board, we'll set it to 84 megahertz, and it should stick to 84 megahertz without any deviation. So in the next few slides, we are going to see how the PLL works. And as a brief side note here, just go to the reference manual. In the reference manual, when you download the reference manual and check, everything that you see here, all the annotations that I have done will not be there in the, of course, the PDF that you download. Okay, so this is something that I have drawn on the PDF for my convenience, so that it is easier for me to explain you the clock tree. So all the comments and everything that I have added, the PDF is actually devoid of all this, so it will not have all of these colors and underlines and all that stuff. So all these, coming back to the diagram, this is a general layout of a phase lock loop. And again, phase lock loop is something that is quite confusing if you do not understand the concept. So as we can see, the phase lock loop consists of 4 blocks mainly. One is the crystal oscillator, that's the reference frequency, and we were talking about the external crystal, the 8 megahertz crystal that we have. That is the HAC clock that we are going to use. So this is the HAC clock here. Okay. Then you have the phase detector, you have a low pass filter, you have the voltage controlled oscillator itself. Now all of this is just to keep the voltage controlled oscillator in a stable position. And then we have the frequency divider. So we will go through each unit one by one. Before that, let us understand the concept of a phase difference. So let's go to the next slide, and we have the phase detector that comes first. So we are talking about this block, which is called the phase detector, and this is one of the main blocks in the phase lock loop. Now, what does the phase detector do? Let's assume that in the PLL here, we have 2 signals going in. One is the steady signal from the crystal oscillator. Another one is the signal that the voltage controlled oscillator outputs, goes through a frequency divider and goes back to the phase detector. So we have two signals coming here. One is, say, is a clean signal from the, though my drawing is not that clean, but just assume that it's a purely stable, say, 8 megahertz clock. And here also we are getting a 8 megahertz clock. Okay, so here it's a, so here also we are getting a 8 megahertz clock. So, but this 8 megahertz clock that we are getting is not stable. So there is phase noise here. So this is going to drift. So, and of course, the voltage oscillator is going to not output 8 megahertz. It's going to output, say, some higher frequency, and probably that is going to be brought down to. So we took 8 megahertz as an example, and you might be wondering, since we are setting it for 84 megahertz and the crystal is 8 megahertz, 84 watt, 84 by watt is equal to 8. So we don't, 84 by 8 doesn't come to anything. Okay, so there are some calculations using which we can actually get that frequency back into the phase detector. So what should be the actual voltage controlled oscillator frequency is something that we will see. So it is not going to be 84 megahertz, it's going to be something else. Okay, so even after this block there is going to be some divider, prescaler out of which the frequency that you will get is 84 megahertz. So we'll come to all that. Okay, so now let's assume that we have two 8 megahertz clocks coming in here, and one is unstable. That is, this clock is unstable. So what happens is, when you have two waveforms, one is steady, another waveform which is unsteady. So when the waveform becomes unsteady, its frequency changes with time. So when the frequency changes with time, the phase of the waves change. That is, from this, so say these waves are completely in phase with no difference in phase, suddenly may just shift. So this wave, because of changing frequency, it might go something like this. Of course, we are assuming that these cycles are of equal length. So maybe the drawing is not depicting that, but that's how it is. Okay. So how do we bring back this particular waveform to exactly be in step with this one, same frequency, same phase, is the job of the PLL. Now let's go to the next slide, and this will be shown. That is, a phase difference will be shown. So let's assume that this is the signal that the crystal is giving out. Say this is 8 megahertz. Okay, and this one, as you can see, say there has been a deviation, and this frequency has become lower. It can become higher or lower, right? So this frequency, it's gone down. So it's the time periods are much bigger, and also this signal is this waveform, the rising edge is actually falling behind the rising edge of the first signal. That is, when this signal goes from 0 to 1, so this signal one rising edge goes from 0 to 1 at some particular time t, the rising edge of this signal is going from 0 to 1 at some time, say t plus delta t. Okay. So something like that. So we have a phase difference here. Okay. Now the job of the phase detector is to detect the difference between the phases and generate an output waveform which represents the difference between these two phases. Okay. So how is that accomplished? when so suppose you have the phase detector circuit like this, it's just, let's assume it's a block, and there are two inputs to the phase detector circuit. Okay, and say there is an output. Now when the any of these signals, so whichever signal goes out first, okay, so for example in this case, say signal 1 has gone from 0 to 1 first. As we can see, this is leading, this one has gone up after this one, so this is leading. The moment this happens, there is a rising edge in the output, and the rising edge stays until the rising edge for the other signal comes up. That is, when the rising edge from this signal comes up, this signal goes back to 0. I hope I'm able to explain it. So the rising edge, when it first goes up, this signal goes up, and the rising edge of the next signal only is able to bring the level back to 0. So rising edge, this signal goes up, and the rising edge of the next signal is able to bring it back to 0. Okay, and the process repeats. So here there's a rising edge first, again this one, and then this rising edge comes, which is later. So there is a gap, there's a phase difference is this, so that is where it creates a square wave with this much width. Again we see that the rising edge is here for this signal, comes first. It could be the other way around, and we'll see such a scenario as well. So rising edge comes here, and then the rising edge of the second signal comes here, so again goes up and goes down. Similarly here and here. So this is what the circuit does here. That is the job of the phase detector circuit. Sees a rising edge, which wherever, so for signal 1, the rising edge is positive volts. Okay. For signal 2, when it goes first, the rising edge is negative volts. We'll see that in the next, or the slide next to that. So this is the logic that a phase detector follows. So a phase detector is a circuit to detect the phase difference between two signals and a output wave representing the phase difference. Some phase detectors are capable of detecting both lagging and leading phases. So we are going to look at the phase frequency detector, which will detect both lagging and leading phases. There are various kinds of phase detectors, like XOR phase detector, which is type 1, and phase frequency detector, which is type 2. We are going to look at phase frequency detectors, and that's what is written here. And phase calculation starts from the first rising edge of either waves. The next rising edge of the other wave is checked, and the duration between these two rising edges is the phase difference. So that is what you saw here. So that is what the circuit does. This is the job of the circuit. So any square wave, two square waves, this is the representation of the phase difference wave or phase difference signal. Now this is the phase frequency detector circuit which does that. Now, without getting into the circuit details, like we saw previously, we will only explain the behavior of this particular circuit. Okay, these are just two D types. So those of you who have a background in basic electronics and digital electronics in particular will understand what a D flip-flop is. And this particular circuit, and this is an AND gate, this is a NOT gate, and this is a PMOS, and this is an NMOS transistor. So, and the output is actually connected to a voltage divider, and this is to keep it, say, somewhere at voltage VCC by 2. So this one is kept at voltage VCC by 2. Now, one thing is, when we will go ahead with explaining the phase lock loop, we will make some assumptions, because we are not exactly aware of how the PLL works how the PLL is designed on the microcontroller. So PLL designs could vary. So I have made certain assumptions here. I might be wrong, but nevertheless, this will completely clarify your your concept about the PLL. So even if the PLL were different and you got to know later, I don't think you will have any issues in understanding the other design also. So anyway, so this has the voltage split up into voltage divided into VCC by 2, and then it goes down to minus VCC. Now this is what you see in the phase frequency detector, and assuming that this signal is of a different frequency than this one. Now in the previous slide we only saw the second signal lagging the first signal, but in this case we will see both sides of it, because this signal is of a different frequency and it is not exactly a proper multiple. The frequency is not an exact multiple. The first two signals are completely out of phase. That is why you will have the phase difference changing over time. So for example, if you had two equal signals of the same frequency but they had a little bit of phase difference, then you would get a signal something like this. We'll come to that. So here also, when this signal goes up first, we have the output going up and the second signal brings it down. One thing we see is when the second signal is leading the first signal here at this point, instead of the output going up, the output goes down, and the up of the second signal again brings back the value to 0. And it's all done by this circuit. So if the second signal leads, we get a negative pulse until another rising edge occurs in the reference signal, and this pulse goes from negative back to positive. And if this signal is leading, the first rising pulse creates a positive pulse here, and then so this is the positive pulse, and then when the second signal goes up, this pulse comes down. So the net output signal or net output pulses look like this. That is for a signal that is of a different frequency, and the phase also varies. For a signal which has the same frequency, both have the same frequency, but there's a phase difference, we will see some pulses like this, very uniform pulses, but it will all be in the positive direction because the first signal is leading the second signal all the time. If you can see that here. So here. So second signal is lagging here all the time. So this is the kind of waveform you see. And this is a job of the circuit. Okay. Now, if the second is leading the first signal, so the variation of this diagram, now second signal is leading the first signal, same frequency, you get a pulse train with all negative values. Okay. So this is VCC, this is 0, say this is VCC by 2. Okay. Something like this. So the voltage will be fixed at VCC by 2 when there is no input, and when there is an input, it will go to either 0 or 5 volts. There is no negative voltage here. So with the second signal leading, this is the wave train you get. All negatives. So coming to the next one, we will talk about the voltage controlled oscillator.